All right, so I think, if I may, I'm going to introduce our speaker today, Ceren Gürkan. Sorry for the pronunciation. She's going to be talking about discontinuous Galerkin methods today. Ceren earned her PhD in 2018 at UPC, Catalonia. Then she moved to Umeå in Sweden for a postdoc, and then she's been as assistant professor in Turkey in Kadir Has University, right? Working always in this topic of Galerkin methods. And then recently she moved as assistant professor here at UC3M. I think it was last year, March. And well, these type of seminars that we are organizing for newcomers to the department are in principle for you to show what you are doing to the community, to the department, and also for us to see and learn what you're doing and exploit and look for synergies. All right. So thanks very much, Ceren, for being here today. Floor is yours. Thank you.
Thank you very much. Thank you. And thank you all for coming, for spending your lunch time in here in the seminar. As Manuel already said, I think you have seen me around. My name is Ceren. I'm currently working as a visiting professor in the aerospace engineering department. Joined in March. And although you have seen me around, which I assume most of you did, I think you don't know much about what I do research-wise. And today's seminar is about to change that. The idea is that I show you a little bit of my research background and to see if we can find some kind of collaborative ideas to work together. So this talk of today will have 3 bits mainly. In the beginning, I'm gonna introduce a little bit a specific type of discretization, a discontinuous Galerkin discretization. I will give a general overview because this is what I have been spending a lot of time for my research activity, this discontinuous Galerkin method. I worked one way or another around this topic. So first we will start with that, and then I'm gonna give a bit more detailed information on what I have been doing, what kind of problems I have been dealing with during the PhD and postdoc mainly. And in the last bit, I will talk about the current and the future projects that I have in the mind. Okay, so let's start together. I think one way or the other, you are all doing a numerical simulation, a numerical model for your research activity. This is what I assume, even if you are an experimentalist, right? You try to verify the results or like compare the experimental results with the numerical results. So somehow we are all doing numerical simulations to us for our research. For majority of them, for majority of you, I think it's just a tool to understand the physical phenomena that you are interested in, to check to do your model and check the results and comment on them and get a better understanding of the phenomena that you are studying. For some others, like myself, our research is fully dedicated on developing some alternative, they call it advanced, I don't know how advanced they are, but advanced discretization techniques that could be used, that could be the background underlying discretization in a numerical model, which will give you more accurate results on a reasonable computational cost. So this is what I do. This is the basis of my research. Rather than using the tools, numerical models to just understand the physical phenomena, okay? And the numerical discretization techniques, there are zillion of alternatives to those. The 4 very basic ones are these ones, the finite differences, continuous Galerkin methods, finite volumes, and the discontinuous Galerkin, although there are many more alternatives. I think majority of you is using one or the other one of these ones that are listed in here. Chronologically, they were also developed in this order. First, we had finite differences for numerical modeling to basically solve partial differential equations. They are really easy to implement. They are really good. You just replace the derivatives in the partial differential equation with this Taylor expansion, and you can build a discretized system, so they are good. they are limited though for the grids that you might have that are unstructured. Okay, so to overcome this limitation, people end up with continuous Galerkin type of discretizations to solve these partial differential equations and do numerical modeling. Continuous Galerkin methods, they are also very nice. They use a polynomial basis to approximate the unknowns that you have in your partial differential equations. This polynomial basis is continuous over the entire domain, so you kind of enforce this continuity in the entire domain. But these continuous Galerkin methods, they fall short on capturing the discontinuities and the sharp fronts, shocks, etc. Because, as I said, their basis is fully discontinuous over the entire domain. So you are kind of pushing to discontinuities to be smoothed out. Finite element method was one very famous method that can be considered as continuous Galerkin. Okay. As they fall short on capturing discontinuities, people end up with finite volume methods because these ones, they impose conservativity in the local finite volumes that you have defined on your domain. So they can easily capture any discontinuity that might be happening within the domain because you are fully local, imposing the conservativity condition from one volume to the other. Okay. However, finite volume methods, they fall short if you want to do a high order, high fidelity simulation. Because if you want to do high fidelity simulation with finite volumes, but you want to capture your discontinuity, you need to include lots of neighboring finite volumes into your scheme, and this increases the size of your computational stencil per se and increases the computational cost eventually, and it becomes cumbersome to do high fidelity simulations. And that brings us to the discontinuous Galerkin methods, which is initially proposed for neutron transport problem, which includes lots of discontinuities. To capture those discontinuities with a high fidelity approximation, people end up with discontinuous Galerkin methods. So now I'm gonna compare these discontinuous Galerkin methods, type discretizations, with the continuous Galerkin discretizations, because that is the fair comparison, because these two can go high order. They have a polynomial basis, both of them, and you can increase the order of this polynomial to get a higher fidelity simulation for yourself, okay? So let's compare these two a little bit more in detail. A typical continuous Galerkin mesh, you can think of continuous Galerkin as finite element, okay? Continuous Galerkin mesh with an approximation, polynomial approximation degree of third order that looks like the left guy in here. And the discontinuous Galerkin, the counterpart discontinuous Galerkin mesh would be like the one on the right. You see that in the continuous Galerkin, you have these nodes defined at every element in your domain, and these nodes, they are shared in the element faces, okay? However, on the discontinuous Galerkin mesh, the elements are fully separated from each other. Discontinuous Galerkin mesh or discontinuous Galerkin approximation is also having a polynomial basis, but that is a piecewise polynomial. So this is broken in between the elements, those polynomial bases that you are using for your approximation in the discontinuous Galerkin. So this is very typical look for the two alternatives that you have for your high fidelity simulation. One thing, of course, to notice really easily is that shared nodes in the continuous Galerkin in between the element faces, while you have them totally separated in a discontinuous Galerkin type of an approximation. In the continuous Galerkin, once more, since the basis is continuous over the entire domain, you are enforcing this continuity strongly, okay, because your basis is continuous, you cannot do better than that. However, for the discontinuous Galerkin, you enforce the continuity only weakly, okay? Your basis is discontinuous, you weakly enforce the continuity on the element faces. And the conservation is, again, globally enforced in a continuous Galerkin discretization and only locally on the elemental level enforced for the discontinuous Galerkin type of discretization. So this mainly separates these two alternatives that you have for a high fidelity simulation that you want to do, okay? this locality of the discontinuous Galerkin, it has advantages and disadvantages. It is good because you can do locally P refinement and H refinement if you are using a discontinuous Galerkin type of discretization, okay? For the elements that are, let's say, close to the discontinuity, you can just refine the mesh over there or increase the polynomial order. This is very natural. For a continuous Galerkin, though, you cannot only separate some of the elements and increase the polynomial order there. For example, that will be more cumbersome to do. So this is one advantage, to have this broken local space for the DG. And of course, they are conserving this DG type of discretization. They conserve the properties at the elemental level. So that's also a nice. They are highly used for the convection-dominated hyperbolic problems because you can play with the element fluxes in the way that you like. Okay. They are nice. This broken space of the discontinuous Galerkin is also nice because everything happens in the elemental level and you can highly parallelize this DG, this type of discretization. However, one very obvious thing is that you are not sharing now the nodes at the element faces, which increases the number of nodes, number of degrees of freedom that you have in your system that you need to be solving at the end. It is highly increased for a DG discretization, and hence your computational cost will be quite high compared to a continuous Galerkin one. For example, if you want to solve an elliptic problem, paying that cost of DG is not really worth it. But if you want to capture a discontinuous problem in a high fidelity, then DG is worth to pay for. Okay. However, there is an alternative for this high increased number of degrees of freedom of the DG discretization. This Cockburn in 2002, they end up with this alternative DG discretization. They call it hybrid DG, where they have defined a new set of unknowns on the mesh skeleton, on the black dots that you have in the bottom figure over there. So you are only solving for those black nodes at the end. So you decrease the number of nodes that you are solving for quite a lot, keeping all the advantages, properties, all this locality of the standard discontinuous Galerkin in the hand, and also not increasing the computational cost as much. So this was like a good alternative to cope with that bottleneck of standard discontinuous Galerkin methods. Okay, so this brings us to what I have done for the research over the past years. What I have done during the PhD, and after that as well, stayed more or less in the same research line, is that I worked on extending this hybrid DG discretization. So remember, what I am looking for my research is a better discretization technique. It will give you a higher fidelity at a lower computational cost. So we have this always pursuing a better, a less costly and a better more accurate solution, right? So that's why we wanted to extend the HDG discretization, this hybrid DG discretization. We extend it how? We extend it by removing the mesh creation costs, meshing costs, and remeshing costs from a hybrid DG discretization. Because when you do a numerical model, one of the biggest issues that you have is the meshing and the meshing costs. If your domain is mobile, even you need to remesh at every time step, which is maybe the most costliest bit of a numerical simulation, right? So we wanted to remove that in this hybrid discontinuous Galerkin setting so that you will end up with a high fidelity solution and without even a meshing cost. How to do that? Okay, so if you have a standard domain, if you want to do it with a standard discretization, what you need to do is to create a mesh that fits to the boundaries of your domain, okay? Like it is fitting your mesh to the rectangle and the circle in here. If one of your domains are mobile, if it's moving, your mesh gets distorted, so you need to remesh, create a new mesh at this new time step to get a nice numerical solution, right? Which is costly. To overcome this, to avoid these remeshing costs and meshing costs for a stationary complex geometries, what we have suggested is to introduce so-called cut discretization into hybrid discontinuous Galerkin setting. What is cut discretization? Cut discretization is this. You have a cheap, easy to create background mesh, and you define your domain on top of that background mesh using a scalar level set function, okay? Such that your boundaries, your interface is cutting through that background mesh, okay? So the only thing that you need to do is to keep track of which elements on the background that you are cutting, okay? If one of your domains is moving, you don't need to remesh, you don't have the remeshing costs. You only need to keep track of which elements now you are cutting on the background on the new time step, okay? That's as simple as that. For remeshing costs, this is obvious, but it's also very useful if you have a stationary domain, but your domain is really having complex features like the curves, etc. Creating a fitting mesh to that domain is, again, very costly. But if you can just define that domain with a level set function and with a background mesh, you will avoid those meshing costs as well. Okay, so we bring this into the hybrid DG setting, okay? Further lowering the computational costs. How to do that? On a very simple elliptic problem, just to give you an idea how the discretization actually looks like. For an elliptic problem, let's say you want to solve it on a square domain with a circular void in the middle. What you do normally is to create that mesh on the right. Fitting mesh. With an XHDG, what we do is that we create a structured background mesh, really cheap, and we introduce this circular void with a level set function. And one of the, let's say, features of discontinuous Galerkin discretization is to rewrite your equation as an equation of two unknowns. Initially, I just have in the elliptic equation my unknown u. But we rewrite those equations in a mixed form. They call it a mixed form, where the gradient of u, your flux, is rewritten as a secondary unknown in your equations. So you rewrite your equations and you set at every element, at every uncut element in your domain, the boundaries are at the boundaries. This unknown value variable is equal to this variable that is living on the mesh skeleton. Remember, this is hybrid DG. I want to write everything in terms of the variable at the mesh skeleton to reduce the degrees of freedom that I will have at the end. For a cut element, you do the same. You will just have an extra condition on the interface. Okay, this is the interface condition, the circular interface that we had in the hand. And typical to discontinuous Galerkin, hybrid discontinuous Galerkin, also continuous Galerkin discretization is that you work with the weak integral forms. So you write everything in the integral form, and you, at this point, you introduce a numerical flux, which gives you a great flexibility on how to define these numerical fluxes, okay? Depending on the problem that you have in the hand, you can play with this numerical flux so that it will be capturing the discontinuity at the element faces that you might be having, all right? In here, I have the unknowns u and q, my original unknowns, plus u hats that are living on the mesh skeleton, that are the hybrid unknowns that are coming from the hybridization process. And I also introduced a new unknown now that is living on this cut interface, which is u tilde. However, you can eliminate u tilde from your system. You can rewrite, doing some matrix manipulations. You can, and using the interface condition, you can write that u tilde in terms of the original unknowns u and the flux q, okay? At the end, what you will have in a HDG or DG or extended HDG discretization is a matrix system, okay? Matrix system that is looking like this guy in here, written in terms of your primal unknown u, the flux q, plus the unknowns that are living on the element faces, the U hats, all right? You manipulate the matrices once more, and you write your primal unknowns U and Q only in terms of that unknown that lives on the element faces, on the mesh skeleton, okay? So you have now written everything that were living, the U's and Q's that were living on the black dots on the figure that you have on the right. Now you have written them for every element in terms of the red dots that are living on the mesh skeleton, okay? For every element we do that, and then we assemble everything together by imposing the flux continuity at the faces, okay? Once you do that, you have a system that only has this unknown that is living on the mesh skeleton as an unknown, and you solve for that, only for that. And then you put back whatever you have calculated for mesh skeleton, you put it back onto the black dots, okay? So you save, you keep all the advantages of this, all the locality, all the H refinement, P refinement properties of discontinuous Galerkin methods, but you were able to write everything on the red dots, so you saved a lot of computational cost, okay? If you bring the cut discretization to this once more, you will also avoid the meshing or the remeshing costs as well. So this is like doubling the advantages, okay? So we developed this, and then we have checked this. So the idea was to prove the concept of this cut discretization actually works. It actually keeps all the advantages, all the accuracy or the high fidelity of the HDG discretization, and we have worked on it on a simple fundamental void problems, and we have seen that the optimal convergence when you do this cut discretization is kept, all the locality is kept, flux conservation is kept, everything is quite nice. We proved the concept on the simple problems where we had an interface. We impose a jump at the interface. We were easily able to capture that jump with no problem, since this is a discontinuous Galerkin type of discretization, and again kept the optimal convergence when we bring the cut discretization to the picture, for this case too. When you have double discontinuity falling inside a single element, this is quite, when the discontinuity is really small, it's really difficult to capture with alternative discretization techniques. But with XHDG, we were able to capture that discontinuity within the element with double enrichment very naturally per se. Doing the same thing with a continuous Galerkin alternative, you would have not been able to capture that discontinuity as sharply as we did for the extended HDG. So these were all to do the proof of concept kind of studies, okay? Which told us, okay, you can do the cut discretization and you can still keep the optimal convergence for your work. But there's always a but. There's always a but. This cut discretization is good. It is keeping all the advantages properties, plus it is saving you meshing cost. Okay, everything is good, but not. Because you have a problem with the cut discretization is that if your boundary is cutting really close to the vertices of your background elements, okay, then you would have an ill conditioning problem. Okay, in the system matrix, you will have very large values and very small values appearing together, and you will have a stability problem. Okay, what to do? There are actually this is another research line. What to do to when you have a bad cut situation like this guy in here. What I have done was actually a kind of a shortcut. Is that we scan all the mesh for any elements that are in a bad cut situation, and for those we just fix the nodes, we just move the nodes that are on the bad cut on top of the interface, like the guy on the right in here. Okay, we just do this scan, but again you are saving the meshing cost, but okay, now you need to scan your mesh to check if you have a bad cut situation or not. Okay, it's not as costly as meshing, but okay, you need to do it. If you don't, if you don't fix that bad cut situation, you are actually losing some kind of convergence order. But once you fix it, you recover back to the optimal and actually super optimal orders of convergence. So you cover back the high fidelity. Okay. So this is one problem of any cut discretization that you might see. Another alternative to stabilize this ill conditioning problem is to add some ghost penalty, so-called ghost penalty terms into your weak formulation, okay? They are specifically designed to extend the stability properties that you have in an element to the cut element, to the bed cut element, okay, and forward. This was already done for a finite element method, cut finite element method discretization, and we have kind of followed the same logic and introduced these ghost penalty terms in a cut discontinuous Galerkin settings. And then, only then, we were actually able to work with more complex geometries in 2D, in 3D, again, recover the optimal orders of convergence. Also, we were able to deal with a bit more complex advection reaction type of hyperbolic problems on complicated geometries, and again, recover the optimal orders of convergence for these rather complex situations or the geometries, okay? Remember, for these geometries, you don't have the meshing costs. You do the cut, per se, and then you just kind of deal with any bad cut situation that you are having, okay? And you have a discontinuous Galerkin background, so you can do high order, you can do capture discontinuities, shocks, whatever that you have, and you can go as high order as you want, okay? So this is what I have spent, let's say, a lot of time for my PhD and postdoc, developing these alternative techniques for any numerical simulation. What I currently do is, well, I currently finished a national project that was funded by the Turkish Science Foundation. In this project, we actually looked for some other alternatives to deal with this stability problem of the cut discretization that I have just told you about. Rather than adding new terms or rather than scanning through the mesh, we looked for some other cheaper, more generic alternatives to deal with that situation. We couldn't really conclude any concrete results, but one thing that we were able to do is to implement this extended cut discretization for linear convection diffusion type problems for convection dominated flows. They were really nicely able to capture the discontinuities with no problem, and this convective flow, they were really accurately described, modeled. We are currently doing the nonlinear convection diffusion, Navier-Stokes type of problems with this XHDG. And I did fund 2 master students and for a very short time a postdoctoral researcher to do this work. This is something that I have been doing the past couple of months. We are still in the pursuit of finding a right alternative on or cheap and generic alternative to how to deal with this cut problem, though. It's just the funding of the previous project is just finished. The other thing that I have planned, which is not in the implementation yet, is to do the aerodynamic modeling of floating offshore wind turbines. I wrote a Marie Curie project proposal with this idea, and I am waiting for the results. Even if I have it or not, I will implement this idea. The plan is to implement this idea. Why floating offshore wind turbines and aerodynamic modeling of them is because I am part of the CFD group here, And they already have some know-how on the small-scale wind turbines. And they already have built this in-house solver, the Gürkan GPU. It's a GPU-based, so it's quite offering some advantages. And the idea is to further enhance that numerical solver that the CFD group has, to be able to model high Reynolds number flows like we would have in a large-scale wind turbine, and also introduce a turbulence model to Gürkan GPU, which currently doesn't have it. We are only doing the low Reynolds simulations at the moment, okay? So this is one of the ideas that I will implement in the coming months and the weeks. And the third thing that I am currently doing is that I'm kind of taking part in the Samara geometry optimization. The Samara project, it has been started long before that I have joined the CFD lab. Actually, one PhD student did full work on this. And the idea is to optimize these flying Samaras and find an optimal geometry to maximize the power coefficient, okay, from them. Initially, for the PhD work, for example, the geometry that was used was the one on the left, the fat geometry. It's more like a blade-like geometry. Now we are looking for more Samara, real Samara looking like geometries, and to see if those ones are better to extract power or not, or they are offering some advantages or not. And initial results shows that yes, you can increase the power coefficient by changing from that fat geometry to the one on the right, but this is still an ongoing work that needs to be concluded. Okay. Okay. So final things that if you are in need for or you are doing a numerical simulation, your problem is highly discontinuous, and you look for high fidelity simulations, possibly discontinuous Galerkin methods is the way to go. Okay. If you need it, or possibly you don't need high fidelity and you are just doing an elliptic problem and you just don't want to spend that much of a computational resources on a DG simulation, that's also possible. But if you are in the first category, we will have very soon, I mean, not very soon, but in a couple of months, we will have a DG type solver, DG discretized solver in the group. And, we can talk about it. The second thing is that if for any reasons that you are interested in doing a simulation that is using that is related remotely or closely related to wind turbines or small scale or large scale wind turbines, again, we are also on track of that, and we can talk about it. Okay, I think that is all from my part. Thank you very much for your time. And any questions, just shoot or come and we talk. Thank you. Yes. I was fast enough, yeah. Right? Yeah.
Do we have? Oh yeah. Super fast. No. Does it now? Yes. Okay. Thank you. Thank you, Ceren, for your talk. Quite comprehensive. Very nice. Thank you very much. Now we have some time for questions, so don't be shy. Questions? All right. Andrew?
Thank you for the nice talk. I've done runs, not DNS, so I don't know exactly what all the differences, but how does your way of cutting the mesh compares with an overset mesh where you have like an internal volume with a mesh that follows the body and then you do the cut? between
You
that
mean
internal
overlapping?
volume.
You do overlapping meshes. Is this
Yes.
what you're saying?
Yes, and the internal mesh follows the body. Yes.
Yeah, that is another alternative when you have a rotating or moving domain, right? Rather than, so what I have presented in here is other alternative. The overlapping meshes is another way to deal with rotating domains, right? So these are two different methodologies per se. Overlapping meshes, they are nice, but what happens is that, so this internal rotating mesh that you have fitted to your body, rotating body, wherever it cuts the outer mesh that you have over there, you need to do some kind of interpolation, right? And that for some simulations that interpolation can actually reduce the order of simulation that you have, the order of accuracy that you had for your simulation. It can kind of reduce it back to some lower order. So that's one, let's say, disadvantage of doing an overlapping mesh for the rotating bodies. But they are more straightforward to implement than this cut discretization or the level set description of the domains. Yes, I agree. And also, yeah, so these are two alternatives. They often, each one has limitations and I think advantages. So to choose one or the other, yeah, it depends what kind of model that you are looking for. Okay, but if you are really seeking for high accuracy and you don't want to lose it nowhere, you have to avoid the overlapping meshes. We can say that.
Okay, Pedro.
Okay, thank you very much, Ceren. I was wondering, I understand that when you go from discontinuous Galerkin to the hybrid discontinuous Galerkin, you eliminate a lot of degrees of freedom because you solve in the skeleton. What is the compromise in accuracy from eliminating those degrees of freedom?
None. Basically,
It's
none.
just for
Exactly. That's exactly what I wanted to. Yeah. So none. You exactly recover. You keep all the accuracy, convergence, super convergence properties of classical DG methods. That's why this HDG, this hybrid DG, becomes so popular. And the only bottleneck per se was these high numbers of degrees of freedom that you have. But with this new unknown that you have introduced on the mesh skeleton, well, there's a bit of overhead still because you still have the doubling of the nodes at the corners, or say at the vertices. So, okay, I don't know if, no, it doesn't work. So at the corners of every element, you are still using a 4 node rather than using 1 node. So it is more expensive. There are still more nodes than a continuous Galerkin type of a node distribution. But compared to standard DG, you don't lose any accuracy or stability or.
So that's great. So
yes.
anybody doing discontinuous Galerkin should move
Following,
to this?
yeah, even if majority is actually switched to HDG and it was straightforward to switch from one to other. If you don't have a solver that is strictly built to do a standard DG type of discretization, yes, they outperform standard DG methods, yes.
Okay,
correct.
Thank you very much.
I think I'll go for a more high-level question. If you go to the wind turbine slide, that was the project you have presented, right, for Marie Curie, you've mentioned.
Yeah.
Good luck. See if you can
Thanks.
get it. Can you elaborate a bit more on what are the scientific objectives, the main challenges you want to tackle, and how your DG discontinuous Galerkin method can help in closing those gaps? So what is Tucan cannot reach that you think with your discretization you could reach in terms of Reynolds or in terms of resolution of the grid, computational times, etc.
Yeah. So we go for this project because one of the strong points that we have is that there is already an in-house solver which is GPU based. So this is a large scale problem. There will be large numbers of degrees of freedom in here, and to be able to solve them computationally effectively, you better use a GPU-based solver. So, and we already had it. So we said, okay, we already have this solver. Let's try to enhance it with a turbulence model. It doesn't have it right now. And also further enhance it with this discontinuous Galerkin discretization. Why? Because currently, to do a high fidelity aerodynamic simulation of these large scale wind turbines, to do high fidelity, you need a high accuracy discretization. You can do or CG with finite volumes. Doing high fidelity is quite cumbersome. It will increase the computational stencil. So the way to go is to DG if you want a high fidelity. And currently, Toucan GPU has finite difference discretization. It's only second order. So the idea is to introduce DG, so I can do high fidelity, and it's GPU-based solver, so we can save the computational cost quite a lot. And we will also introduce the turbulence model that will help also for any other future models that want to do, etc.
But why do you need the high fidelity for this type of problem? This is offshore wind turbines of 5 gigabytes, gigawatts,
Yeah.
I guess. So why do you need that? It's not studied, or
It's not, basically
characterize
I agree that for some, or for, let's say, industrial applications, one actually might not even need to bother to have a high fidelity simulation. Yes, they are already doing low fidelity simulations of this. There's actually a software that they can do that. But to push the limits of science and to understand how these large scale wind turbines, aerodynamics, these intrinsic per se aerodynamic features that are happening that we don't know at the moment with these low fidelity simulations, our idea is to discover those. And one last bit of actually this Marie Curie project is to optimize, again, something also really related to what I am doing, is to optimize the blade geometry because of this, let's say, new know-how that we will create that was not seen before using this high fidelity simulation. We can maybe really optimize the geometry of the turbines as well to increase, again, the power coefficient in the... So this is one idea. One of the last work packages that I have is that.
Okay. Thank you. Last question?
Okay. Well, thank you, Ceren, for the nice talk. Following up on Manuel's question, I didn't understand well your approach here. So you want to use the hybrid DG in Toucan, but from my understanding of programming, this is not a small change. If Toucan is in finite differences, you are basically writing a new program.
Yeah.
So you are keeping the name, but probably you are just
Possibly
keeping the name.
Possibly we changed the name.
No? Is that right, or are there many elements of Toucan that you can reuse with this new discretization?
No, you are totally right. It's basically redoing it. Yeah.
Okay.
Yeah, changing the entire special discretization. Yes.
All right.
But okay, the framework, let's say this GPU base that the Toucan has, we will keep all those things. But
so there are elements that can be somehow abstracted and reused.
Recycled. Yes.
All right. Okay. Thank you.
If there are no more questions, I think we can thank Ceren again for the talk.